Good afternoon. My name is Brandon Ennis. I'm a researcher in the wind energy department at Sandia Labs. And today I'm going to be presenting on a specific wind turbine that's been designed for floating offshore wind sites. So this is the ARCUS vertical axis wind turbine. So just to start here with kind of the motivation and key takeaway perhaps of this presentation. So offshore wind energy is too expensive. In the US, this is especially true. So this past year, that was, problems were realized associated with the cost, the high cost, low margins of offshore wind energy, where the power purchase agreements were too low relative to rising costs. And part of the reason for this is due to the evolution of the wind energy industry, and that wind turbines that have primarily been developed for land-based sites are suboptimal when you move to floating offshore sites in deep waters. To illustrate this point a bit, showing here a graphic from the organization Lazard that publishes this unsubsidized analysis for the levelized costs of energy for various energy generation sources in the US. And shown here for wind energy, you can see moving from left to right the levelized cost of energy range in the US based on resource for that specific site goes from 2.5 cents per kilowatt hour to just over 5 cents per kilowatt hour. As you move to fixed bottom offshore wind in shallow waters along the US, this would be the East Coast, the estimated midpoint for the LCOE is just over 8 cents per kilowatt hour. And then moving further to the right, for floating offshore wind, this very new emerging market that has a lot of, that would be the West Coast in the US, the Gulf of Maine, many countries globally. The cost goes up to 15 cents per kilowatt hour, $150 per megawatt hour. And what you'll notice here is that as these costs increase for these newer industries of offshore, fixed bottom, and floating, that the turbine itself looks very similar, almost identical. And there are some distinctions, of course, but that there really hasn't been a rethinking of what is the optimal wind turbine for these new applications. Using horizontal axis wind turbines for floating offshore and more generally for offshore sites. The first big challenge is that the high mass properties of horizontal axis turbines, this challenges the platform design, which requires more mass and more costs be placed into the platform just to support the system. And that these mass properties worsen as you move to larger and larger systems. So it becomes more of a problem with larger systems offshore. This results in a high levelized cost of energy relative to alternative generation sources in the US. And then finally, when energy is extracted from the wind through a wind turbine, the downstream wake, there's a deficit of the momentum in the wind, that's called the wake, and that persists very long distances downstream of HOTS in offshore environments. So this requires the turbines to be spaced further apart, which then requires much more area offshore and limits the total generation capacity within these constrained lease areas. So we theorized a while back that vertical axis wind turbines could be a solution for this future market. And really because of the unique cost drivers and the design distinctions for VOTs. So for floating offshore wind, the platform itself is the largest single contributor to the cost. And then the turbine cost, it represents only 20% of the total cost of the system for floating offshore sites relative to 50% on land. So based on these distinctions in the costs, really the objective of the turbine should be how can I reduce the platform costs as well as increase the energy production while limiting drivetrain at the bottom of the rotor instead of 150 meters above, above the base of the platform, which greatly lowers the center of gravity and can help to reduce the costs. So just recently, in the last 3 years, we had a project funded to study a new type of vertical axis wind turbine. We call it a towerless vertical axis turbine. The ARCUS rotor, what it's doing is it's replacing where there would be traditionally a rigid steel tower at the center of the rotor. It's replacing all of that mass with blades that are bent into their shape and then held in that position through tension center supports. So ARCUS is Latin for bow. So very similar to how a bow functions, this allows for an efficient utilization of the materials and the ability to shift away from certain loads that can be more catastrophic, so that you can remove some failure mechanisms. Through the project, we compared this specific design concept with alternatives. So the first alternative is the traditional towered Darius Vought. So we compared this to an available reference that from earlier work at Sandia at a 5 megawatt scale, and we found that moving away from removing that tower and designing this ARCUS rotor, that we had a 50% mass reduction in the rotor itself. And then comparing at a utility scale, so at the same swept area, it's kind of a 12, 14 megawatt horizontal axis wind turbine. We find mass advantage there as well, where there's a 30% mass reduction for the turbine compared to a HOT at a much lower, 70% lower elevation. And also the opportunity project where we were designing the turbine and the platform simultaneously. And through that project, we identified a specific platform architecture called a tension leg platform. So this is one of the newer platform types, fundamental types in the oil and gas industry, that's known to have the lowest mass requirements for the hull itself, for the platform. But the challenge of this type of platform with the horizontal axis turbine is that it requires the top side to have a low center of gravity as well. So we found that there's an optimal pairing between the vertical axis turbine enabling this type of floating platform to be effective for floating wind while having still simplified installation processes. So then the top 3 reasons to develop the ARCUS vertical axis wind turbine. The first reason is that the turbine itself has significant reductions in mass and cost relative to horizontal axis turbines, as well as increased energy production than what would be optimal for a horizontal axis turbine, where if you need a larger generator for a horizontal axis turbine, the mass of that generator, that increase, would be more substantial to the turbine costs and the platform costs. The second reason is that the low mass properties of the turbine enable this specific floating platform, tension leg platform architecture, which has known benefits from the oil and gas industry and can really simplify both the installation as well as the operation of the system, having very low motions in operation. And then finally, an additional advantage, which isn't directly quantified here, is that vertical axis wind turbines, so this obviously allows for developers to increase the revenue from a specific site, as well as where there may be land constrained, offshore land constrained areas, to increase deployment capabilities there. Well, thank you for your attention. And then, we're looking for partners of all sorts as we continue to pursue funding opportunities, both private and public, to continue advancing this technology and hopefully see it come to market in some distant future. So thank you.
Interesting presentation, Brandon. I'm curious, it sounds like your patent strategy is to create some IP for the platform and for the turbine assembly. Is that correct?
Yeah, that's correct.
It is the prior art. I couldn't tell from the pictures in that slide. Is there prior art in the vertical turbine assembly? Because clearly in the horizontal, we've seen that all over the place for many years, but is there a lot of prior art here, or is that a novel invention?
For the towerless
for the turbine, yeah, the vertical axis.
Yeah, so we have a patent that's been issued for that designation of it being a towerless vertical axis turbine with the pre-stressed blades, tension center supports. So that's been issued. We filed for that in 2019. It was awarded in 2023, I think. So it took a while. All of the other patents have, are moving through more quickly. But yeah, as far as this is a novel approach that was issued, that's a U.S. protection. There are so yeah, we'll continue, looking for funding so that we can develop the technologies that I think would be more in the lines of controls at this point. But yeah, there are certainly patents available. The Darius type turbine, which traditionally towered, has been around for a very long time. But yeah, there's very much still opportunity to innovate and file additional, especially follow-on IP.
Okay, and last question for me, where are you on product market fit? What sort of evidence do you have that this is a commercial product?
Yeah, so there are definitely challenges that are distinct that weren't highlighted here, but are in a longer slide deck. The developers very much feel the pain of the industry. They understand the challenges with horizontal axis wind turbines. There are only 10 floating horizontal axis wind turbines installed in the world right now, and the first set was a set of 6, and all of them have had to have gone back to shore for operations and maintenance due to failure, probably because of the exaggerated motions that's distinct for floating sites. So I think the industry is realizing the challenge. Definitely the cost challenges are apparent, but the technology is very risky. So getting a turbine OEM to develop this on their own, I think would not happen. But developers seem more interested in funding innovative turbine technologies, although probably, certainly at a higher TRL than where we currently are.
Good work, Brandon. Have you looked at combining or done the analysis
axis turbine I'd mentioned is bigger generator, so you end up capturing more energy in high wind speed situations, which at offshore sites resulted in 45% more energy, but then it's a lower capacity factor. So when you get down to electrical transmission offshore, if you need a high utilization rate of the pipes, then you would want to combine this with either fuel generation or battery storage.
Thank you. This is really cool to hear about as well. Just, as we emerge into more of the green energy spaces here. But my question, as I think about and I look at the presentation here, I'm more curious about the manufacturing process of all of this and put together because, we've seen in the past of like supply chain management. And is there any color that the team can like add about how this is, being worked out in when we look at the whole production of this? And because I'm thinking about like scalability for this and, what is the process with that?
Yeah, great question. So yeah, supply chain. So we use a lot less steel, which is a benefit. So the turbine itself uses very little steel compared to horizontal axis turbines. No steel tower. The nacelle that's above the tower for HOTS is really massive as well. We don't have that. It's just in the platform. The platform itself has a low mass relative to alternatives. So less steel, which is good. So it's a bit buffered from the volatility for that material. The blades are the big manufacturing challenge. The blades here are 3 times longer than they would be for a horizontal axis turbine. Just they sweep the perimeter versus the radius of that swept area. So you have to but it is, yeah, it's a great challenge.
Brandon, excellent presentation and love your energy. When I was getting impressed by this technology and so that this is a technology which is hot, and then you made me say what? Speaking of that, my question was actually stolen by Ward, the second question. So I have to come up with a new one. In terms of most of the startups, going back to the product market fit, fail because of that one single reason. They did not have the product market fit. Do you think it would be prudent to engage some of the ONG pioneers and then kind of involving them as part of not just the design process, but also the feasibility, the implementation, the material procurement, or maybe kind of looking for new materials and a composite alloy material that would help it kind of become reality? And I know that this is going to be a very capital intensive. So have you thought about engaging them proactively rather than this being, okay, I have it, now hammer looking for a nail?
Yeah, and we have. So yeah, several of the big oil and gas majors have expressed interest. Some we've reached out to, some that have reached out to us. But yeah, it's interest until you ask them to participate currently. But I do think as far as finding a market, the big challenge, like you said, this is a very hard problem. And the big challenge is how do you scale this up? That you go from a low TRL to then the largest turbine machines in the world. And the idea is that maybe there's some intermediate products, and you would need to do that in your development timeline anyways. So can you develop intermediates that actually have a market? That be an approach taken for new turbine technology.
Yeah, it's like an intersection and kind of adoption to find that there would be a potential integration with respect to what you have come up with and the infrastructure that is crippling and failing because of the sheer age. So good luck.
Yeah. Thank you all so much.
Thank you.